welcome. Thank you for inviting me. So I'm talking about non-planar printing for stretchable tactile sensors. So my work is not about hydrogels. I think I'm a bit of an outlier here. And yeah, tactile sensing, we just heard about it. Why do we need tactile sensors? I'm more from the robotics background. So I'm from the robotics chair at TU Munich. And for our robots, like the next generation of tactile robots, should have tactile sensors over the whole body that can measure the mechanical interaction forces with the environment. So contact points, 3D force vibration, multimodal sensors. These can then be used in the robot's central nervous system to do sensory motor control for exploration, manipulation, and response tasks. What are the requirements for tactile sensors? So there's a big manifold of requirements here, which has been discussed before as well. So one is definitely conformability, stretchability, and softness, especially for grasping, as you need like a form closure when you do grasping to have a stable grasp, but also for the integratability into curved surfaces and any kind of objects. On the other side, you have the sensing requirements. So you want good accuracy and high signal to noise ratio, and also high frequency responses from up to 1 kilohertz, which kind of interfere with the softness of the sensors in some ways, at least with like traditional systems. So my research is focusing on the stretchability, of implementing stretchable tactile sensors into robotic systems, and how we can do this with 3D printing technology, so that we can achieve sensors that could be implemented onto a whole robot body in the end. So yeah, like my previous work was focused on stretchable tactile skin using embedded 3D printing, whereby the sensors consist of silicone and a liquid conductive ink, which is encapsulated inside the silicone to achieve very high stretchability. I have like one probe, you can have a look at it. I will give it out. So it's very, very stretchable and can be 3D printed. The resistive transduction method is probably quite commonly known here. So because you have this like liquid cable, and then when you strain it or if you pressure it, you change the diameter or the length of the cable, and thereby the electrical resistance. In my prior work, we then to adapt it to various kinds of objects and robots, developed an automatic framework where you could put in the STL file of any kind of object, and in the end would get the skin with the sensor patterns that can be then directly implemented on the objects to have like a more automated process, and not needing to be able to design every little sensor for every implementation. So what is the problem with this? There's still one thing that is manual, which is wrapping this sensor around the object, which is kind of a lot of work, and also has precision issues with it. So therefore, I come to my work, which I'm presenting today. So I would like to print these resistive pressure or strain sensors directly on the curved surface instead of printing a flat sensor that then needs to be wrapped around it. So we did some research on how we can do this. With like traditional 3D printing or direct ink printing processes, the problem is that if you put a curved object into the slicer, which generates the G code for the machine, then it is sliced into layers, and therefore I think I can use this here, yeah, and therefore your sensor will have like an error in the step, and it's not a continuous line, which will give you inaccuracies in the sensing, and you might even run into issues that these lines might not be connected. So what we did is we had a look into like what kind of continuous non-planar printing methods are out there, and there are already quite a few. But the problem is that none of them gives the opportunity to do curved non-planar transformation compatible with slicer software that is already out there, because this slicer software gives you very nice opportunities for parameter optimization. It is very useful to use that and not have another program where you have to manually code the G code for the machine. So that's what we try to do here, we are trying to do this with curved non-planar transformation. And yeah, this is basically the content of the paper. So first, we did the sensor design, which is just for a feasibility study, like a fingertip shape with a U-shaped sensor inside it. And then we conducted a non-planar transformation of this, got the G-code for the printing, printed the sensor, and made the electrical interface, and then evaluated the pressure sensing behavior, because pressure sensing is actually more difficult than strain sensing with a robotic setup and a 3-axis posture. Okay, so let's go into the non-planar transformation. How does this work? So we have the STL file of an object with a curved surface area, and then we transform this object into a planar surface. This works with 2 functions. The first function is to compensate for the distance from the x-axis. So here is the distance, right? And this should be transformed downwards to the x-axis, which is this function. And then the next function compensates for the longer surface along the x-axis between this and this object, so that we can kind of consistently have the volumetric amount in the final sensor. So then that leads up to this transformation function. And then in the next step, you can just put the transformed STL, it's just a Python script basically running over it, into the slicing software. And that will create you the G-code with all the printing parameters that you would like to change. And then you back transform this G-code into the curved object, which then goes into the 3D printer. And this back transformation was just done with a numerical approach. Okay, so this I have this in a video now as well, so just so it's more clear. So basically you have the object, you transform it to the planar surface, then you slice this in the G-code, get the G-code, and then transform that G-code back. Here you see how the machine is then printing the curved part using a silicone direct. Okay, and a bit more about this manufacturing. So it's a multi-material printing process. So we have 2 print heads. One print head uses dragon skin silicone parts A and B, 50-50%, and some CVEX to improve the printing properties of the material. And then the second print head, which has the carbon grease, which is an off-the-shelf, quite cheap material, which is perfect for prototyping, I think. But to advanced sensor behaviors, we would look into different kinds of materials in the future. Then we optimize the printing parameters for the print process and do the printing, whereby layers 1 and 2 and layers 4 to 5 are just silicone, and in the middle, layer 3, we print the carbon grease. In the end, we have this fingertip shaped sensor and use conductive thread to sew the electrical interface, because we found out in prior research that just plugging cables doesn't really work for liquid ink. Okay, so that worked. And then we did the experimental evaluation of the sensor. Here you can see that we did linear loading of 5 cycles, applying 10 Newton of normal force, and on the y-axis you see the sensor response in %, meaning delta R divided by R0. You can see there's quite a lot of drift, about 40%, and hysteresis of 15%. So this drift and hysteresis, in my opinion, I mean, that's a theory, is due to the very viscous property of the carbon grease, and could be improved with other kind of materials and sensor structures in the future. And then we also did quasi-static loading to see how the relaxation of the sensor is behaving. So when we apply a pressure of 10 Newton, you see that the sensor response decreases. And there is a relaxation of about 50% there. And then something very interesting, which also comes up in other papers, is that we had a secondary peak at unloading from the sensor. Exactly. And then we also did dynamic loading to see how the sensor behaves when we apply different frequencies. And you can see that it does behave differently. So there's a offset between the first velocity and the third velocity. And also we see that in the higher velocities, there's like a saturation. So the sensor response doesn't go all the way up as it does in the first linear loading experiments. So all these behaviors would need to be researched further to improve the sensing behavior. But yeah, to sum things up, we showed that our method for non-planar printing and slicing of curved surfaces worked pretty well. We were able to manufacture a sensor, and we implemented it with a resistive stretchable pressure sensor with liquid 3D printing. And in the future, I would like to improve the sensor accuracy, hysteresis, and drift, and also implement multi-model sensing with, for example, different materials or different sensor structures. And also call out here, because I'm not a material scientist, this is why I'm using this pretty simple material. And I know there are many material scientists in this community. I would be very open for collaboration in that. Thank you very much.